Hello everyone, I hope you and your family are doing well. I am Gyanendra Kumar Sa. I'm currently doing my PhD in University of Rostock. Here again I have come with some interesting videos related to converter control design. In this video we will learn how to get Bode plots from the given transfer function and the physical meaning of the bandwidth of the system. So if we have higher bandwidth, then what it means; if we have the lower bandwidth, then what it means. So this is a general definition of your transfer function, and this g of s could represent anything. So it can represent either your filter, so it can be your low pass filter, high pass filter, resonant filter, band pass filter. It can be any filter. It could also represent your closed loop transfer function. So let's assume you want to design your controller, and then you can also find the closed loop transfer function. So this g of s could be your closed loop transfer function. It could be your open loop transfer function where you want to use a gain margin and phase margin techniques to tune your controller using open loop transfer function, or it could represent your actual physical plant system. So it could also represent your actual hardware. So let us consider one example where we have chosen the low pass filter, and the transfer function for the low pass filter can be written like this. And you can see here your the pole is placed is basically minus omega naught. So this is your pole, or you can call it like an eigenvalue. So it's up to you what you want to call. So the main objective of low pass filter is to filter out our noisy input signal to the less noisy output signal. So that is the main objective. We want to filter our high frequency noise signal. So the desired component can be your AC, DC, or it can be both. Or the noise, the high frequency noise component could come from your switching of the converter. It can be from the sampling of the sensors, or it can be from the interference between the two systems or the two converters, or there are many more sources for high frequency noise signals. So the main objective of the low pass filter is to attenuate this noise signal. So let us see how we can get the Bode plot, which is very simple. You can simply substitute s equal to j omega, which you can also clearly see here. The s is replaced using j omega, and then using complex mathematics operations, you can find its gain, which is this absolute value of this transfer function, and then you can find its phase, which is basically the phase angle of this transfer function in complex domain. So here omega is this omega. It represents your x-axis for the Bode plot. So this is your x-axis for Bode plot. So it's up to you whether you want to use omega or you want to use your frequency, because they both are related. So you can use either the frequency as a x-axis, or you can use a radians per second, or the angular speed in radians per second as the x-axis. So I like using frequency in hertz. So I have chosen here the frequency as the x-axis. And then we would like to find the value of gain and the phase, and we plot them. So this is your gain plot, this is your phase plot versus frequency, and this is nothing is called your Bode plot. So it's very simple. You basically replace s equal to j omega, find its gain, phase, and phase expressions, then you can simply plot them, and you get your Bode plot. So let us consider few important points in this Bode plot. So in DC, so when you have a DC signal, you're basically omega is equal to 0, and when you substitute omega equal to 0 here, you can clearly see the gain value is going to be 1, and your phase value is going to be 0. So since this is a logarithmic scale on the x-axis, so we cannot show you the exact zero frequency, but you can see near zero frequency your gain is gain is 1, and your phase is again close to 0. And let us consider one example where your omega is equal to your omega naught. Okay, so when omega is equal to omega naught, you can clearly see your gain value is basically omega naught over root 2 omega naught, and this becomes 1 over root 2, and this is your 0.707, and your phase value is basically minus tan inverse of omega naught over omega naught, and this is your minus 45 degree. So you can also clearly see from this example. So here omega naught I have considered 300 hertz, and you can see the gain value is 0.707 and your phase value is your minus 45 degree. Okay, and this point, so this the frequency at which your at which the gain value is about 0.707 is also called as the bandwidth or cutoff frequency or corner frequency. So so this is one design parameter. So this is called the bandwidth, and this is one design parameter for your filter, or it can be design parameter of your controller. Okay, and you can vary this bandwidth. So you can see below this frequency the gain of the input signal is higher, and after this frequency you can see the gain of the frequency gain of the higher frequency components is reducing further. For example, you can see if you have a 3 kilohertz signal in the system, then you would see like its amplitude will be multiplied by a point like 0.099, and then you would see the attenuated value in the output signal. And I would like to mention that this Bode plot is obtained actually using steady state values. So this is the steady state analysis, and this analysis in your frequency domain. Now let us consider the time domain analysis for the same Bode plot which we saw before. So this is our same system, and I have again taken the same bandwidth for the Bode plot. So it's again 300 hertz, and you can see the corresponding the same graph. And let us consider this input signal has the two signal. One is your desired signal. So this is our 50 hertz signal in our system, and I have chosen the gain as 1. Okay, so you can also see this red curve. So this red curve is your XD, which is our desired signal, and the gain is 1 per unit. And yeah, and let's consider it has a noise. So noise is like 3 kilohertz noise, and it has gain as 0.2 per unit. Okay, so it's just a 20% gain or 20% noise in the system, which you can see from this black curve. This is your X of t. So this X of t, you can see it has your fundamental 50 hertz component, and it has the noise of 3 kilohertz 0.2 per unit. And you can see the green curve. This green curve is your basically output. This is the output of the filter, and you can see the green curve has the very less high frequency component, and it is because this because of this very low gain at the high frequency component. So it means your noise signal, or the amplitude of the noise signal is reduced in the output when compared to the input. But there is one more interesting thing to observe is that, okay, the magnitude of the noise signal is reduced, but if you can see clearly, there is a phase lag between the input and the output signal, right? So there is this delta T difference between the zero crossing of the signals. And if you would like to find the phase lag between these two systems, then you can use this simple equation where T is your time period for the one fundamental. Okay, and using this example, I have used this MATLAB scope cursor, and then you can find the delta T here. And using that delta T, I try to find the angle, and it is minus 9.82 degree. And which you can see it's again matching with this one. So I didn't using this hand. So of course, this delta T is prone to some error, but you can see they are very close. So this is how so this is one way you can understand your influence of Bode plots in your actual time domain system. So you get the less magnitude of the noise in the output, but you see the phase difference, the significant phase difference between your output signal and input signal. Yeah. Now let us say, okay, you want to tell, okay, I don't want the big phase lag between my input and output. Then so the very simple thing is you can simply increase the bandwidth of the system. So now you can see here the bandwidth is increased from 300 to 600. And of course, you can you can see that the phase lag, the phase is also reduced. And this we can again verify from our same tool chain. But now the interesting thing is, since you increase the bandwidth, what has happened that the gain of the higher frequency component has increased. So earlier it was 9%, but now it has gone to 19.6%, and which you can also clearly see from here. So you can see that the green curve has the higher frequency, like it has the higher amplitude of the higher frequency component when compared to the first graph. And this is expected because you can see the same thing in the Bode plot. Okay, so this is what happens if you choose the low frequency bandwidth, then your the filtering is better, but when you choose the but the phase lag between the input and the output desired component is more. But if you choose the higher bandwidth, then you have the less phase lag between the input and output, and you see more noise in the output signal. So this is for the 50 hertz filtering. For DC, you would not see any phase lag because it does not make sense to say phase lag in the DC component. But if you wish to filter your 50 hertz component, then I would prefer you to go to resonant filter. And the very good resource to learn about these basics of resonant controller is this paper. So I would ask you to go to this paper if you wish to find more detail about the resonant controller. Okay, so that was about the bandwidth of the low pass filter and how to get the Bode plot. Now let us consider the general system. So this can be a low pass filter, or it can be your closed loop transfer function or open loop transfer function. So let's consider one general expression. So this is for your first order system. We would like to focus on first order system. And of course, you can see it has the pole, which is omega p. And I have considered the 3 different pole locations. So this is one pole location which is near 0, and this is another pole location which is far away from 0, and this is further far away from the 0. This is our S plane. So your S can be in general written as the real component and the imaginary component. So this is your real part and this is your imaginary part. And yeah, so this is our S plane. Now let's see the step response of this first order system. So the step response you can simply obtain by writing the x of s over some constant over s. So here I have done the unit step. If it's not unit step, so it could be something like this, x of naught over s, but x of naught I have considered as 1 just for simplicity. And then of course y of s is the product of g of s and x of s. You want to find the response in time domain, then you can take the inverse Laplace transformation and you get expression like this. And this expression looks very similar to what the expressions which we used to see for the inductor current transients or the capacitor voltage transients. So this is like a first order, this is like exponential rise of the signal, and you can compare the tau. So you can compare the both equation, and then you can find the relation between tau and omega p. And here tau is basically your time constant. So what you can see is your time constant is inversely proportional to your pole. Now let us study what happens if we have what happens for these 3 cases. So here you can see the graph and their label. So this is for omega p1, this is for omega p2, and this is for omega p3. So you can clearly see as the omega is increasing, what's happening. So as omega is increasing, what's happening? The response is getting faster and faster, which is also expected because the tau is inversely proportional to your pole in this case, or let's say in the bandwidth. Here the pole and bandwidth are same for the first order system. So if your bandwidth is higher, then your time constant is lower and it goes to a steady state very quickly. Okay, So what we can conclude from this, if pole is placed near origin, you have your slow response, but you have strong filtering. So which we also see from the previous slide. And when the pole is far away from origin, you see the fast response and the weak filtering. So when I say weak filtering, it means you will have the more amplitude of the noise signal. So this is about the pole placement for first order system. Let us consider the second order system. The general transfer function for second order system is given above. Here, omega z represents the zero of the system, and omega 1 and omega 2 represents the pole of the system, which we can also see in this S-plane graph. Here, the very basic assumption is that omega 2 is greater than or equal to omega 1. To understand the unit step time response of the second order system, let us consider one example. So this second order system can be rewritten as the superimposition of two first order systems. And this coefficient A and B you can find simply by following the basic mathematics for partial fraction. These are the same steps which we discussed in the previous slide to get the time response of the output signal. And here you can see the output signal has two components. So the one component is because of the one eigenvalue, and another component is because of the another eigenvalue. These are the nomenclature used to show the components of the output time response corresponding to the corresponding eigenvalues. Let us now consider an example. In this example, we are going to fix omega 1 and we are going to vary omega 2. Here, omega 1 is kept at 100 Hz and omega 2 is going to vary based on this table. And here we are just seeing the result for the first case. You can clearly see that the output response due to this omega 2 eigenvalue is quicker when compared to the eigenvalue omega 1. And this we can understand from this relation which we saw earlier. So our tau is inversely proportional to the real component of the eigenvalue. And since omega 2 is greater than omega 1, our tau 2 will be less than tau 1. And hence we get the output response quicker for the frequency omega 2 compared to the omega 1. This is another example of step time response where omega 2 is equal to 5 times omega 1. In this waveform also you can clearly see that the output response due to the omega 2 eigenvalue is faster. In this waveform, we have the results for all the cases listed in this table. Here you can see that as the omega 2 is increasing, your response is getting faster and the overshoot in the system is getting lower. So we can conclude that when omega 2 is placed near omega 1, then the response is slow and we have the higher overshoot. And when omega 2 is far away from omega 1, then we get fast response and we have low overshoot in the system. Now let us see how we can tune the bandwidth of the second order system around frequency omega BR. This could be an input from a designer to you, and you would need to tune the bandwidth of your second order system around this frequency. From our previous slides, what we know is that the transient response due to the second eigenvalue is faster when compared to the first eigenvalue. And if we assume the second eigenvalue is placed far away from the first eigenvalue, then we can approximately tell that our bandwidth is going to be placed around frequency omega 2. And the very basic thumb rule we can use is omega 2 is greater than or equal to 10 times omega 1. Here we have the bandwidth of the different cases. So this is for this case we have omega 1 is equal to omega 2, and for this case we have omega 2 is equal to 5 times omega 1, and for this curve we have omega 2 is equal to 10 times omega 1, and then for this case we have omega 2 is equal to 20 times omega 1. And you can clearly see that the omega 2 is placed at 100 Hz. And if you see the bandwidth, then the bandwidth is not very far away from the intended frequency. So let's assume you get the 100 Hz as your intended bandwidth, and then you just make this equal to your second eigenvalue, and then the first eigenvalue you can assume as your the second eigenvalue over 10, or you can assume second eigenvalue over 20, or you can keep on go, you can make it 50 times, or you can do like this. And then what you see is your intended bandwidth will be placed around the frequency omega 2. So this is how you can tune the bandwidth of the second order system around frequency omega 2. Okay, so let us now list our observation. So what we know from the first observation, if bandwidth placed near origin, then we have the slow response and the strong filtering. If the bandwidth is far away from origin, we get the fast response and weak filtering. And for PI tuning, for the first order system, your bandwidth is basically nothing but your eigenvalue, or it's basically the pole location. And for second order system, if bandwidth is your design parameter, then you can simply use this thumb rule to tune your bandwidth around omega 2. I have made a series of videos to explain cascaded control design for DC-DC converters. Here is the link, and I would also put the link in the description, so you can look into a description to find the link. So this video, this series of videos explain in detail how you can design your inner current control loop, outer voltage control loop for both in discrete and continuous time domain. I have also validated the controls using MATLAB Simulink blocks. So if you want to learn the basic tool chain to design your controller in discrete and continuous time domain, and then how to implement them in MATLAB and Simulink, then you can follow this video. Thank you very much for staying with me. If you enjoyed watching this video, then please like, subscribe, and comment, and share with your friends, your colleague, and your students. Thank you very much. See you next time.